Okay, well, thanks for all coming out. Today I'm going to talk to you guys about a data pipeline that is kind of an abstract pipeline that you can reuse for all kinds of data. I'm new to analytics in general. I've been probably messing with data analytics for, I don't know, maybe roughly 8 months with R. And so I'm learning how to program with R. I'm learning what type of statistics to use. I'm learning the nuances of the hardware, things like that. So bear with me if this might be a little bit too introductory, but I hope that you can get something out of this. With that being said, I'm going to talk to you about my background slightly so you can get an idea of who I am. Like I said, I'm Mark Gingrass. I work over at Tinker Air Force Base. What we do is data analytics for the supply chain for the entire Air Force, so globally. We have a lot of data to use, and what we typically have been doing in the past was finding top 10s of different metrics, top 10s, top 20s, give me your metrics, and we are trying to get out of that business. We're trying to catch up with the commercial world. So they brought in a data analytics flight. It's actually called the Data Science and Analytics Flight. And we have recruited quite a few people, but what we did was we brought engineers together that really didn't know data analytics. So we're all learning really quickly how to do this stuff. And so that's why I'm glad groups like this exist, so that we can help and get help from other people as well. So today, I'll talk a little bit more about my background. I'm going to go over what a pipeline actually is for data. And then I'll dive into some actual functions and some code. Not going to get like too much into the nuts and bolts, but kind of an overview. And then a couple of tips and hurdles that I've come up with through just working at Tinker, saying, hey, I've run into these problems, how did I solve them? And then I'll take questions. So my programming background, just so you guys know, is I took academic level C++, C++ all the way through object-oriented programming, polymorphism, template programming, but not enough to really make it stick. But the fundamentals I've learned from C++ for coding in general is truly invaluable. So learning R, I'll tell you, there's definitely a learning curve, mostly because I really liked static data types and the strict rules that C++ had. It takes some some practice to get the R syntax and language down. And it's one day I think I have it, the next day I feel like I'm lost. I'm lost all over Stack Overflow, and I have like 15 Stack Overflow tabs open. So I've got a bachelor's degree in aviation management, an MBA degree, and I'm now pursuing a Georgia Tech master's in data analytics. I have a lot of computer science background and math background, but I never got a STEM-related degree, so I'm excited to actually pursue something that I can call it a STEM degree, so I'd be excited about that. So I was active duty for the Air Force fixing electronics. Then I worked at Tinker fixing electronics, so I did some troubleshooting, some basic programming there. And then I moved over to this world called forecasting. So we're forecasting for the future. And so it was kind of my taste of getting on the management side of things. I became a logistics manager, trying to glue things together that didn't work, all in supply chain, mind you. And then finally, that leads me to my current job. It's an operations research analyst for Tinker. And we have about 14 analysts, and I think maybe 4 or 5 of them are interns. And we're growing. We actually just got 3 contractors as well, and we're going to grow to 7 contractors. So be on the lookout on usajobs.gov if anybody's interested in jobs. The series that it's called is 1515. So with that being said, my next move is probably going to go to the FDA, and I'm going to do data analytics for them. So that's pending. We'll see. Okay, so let me start by showing you guys a data pipeline and tell you what it really is. Data pipelines are really crucial for data analytics. What that means is we have to bring data in, raw data from all sorts of different sources. We have to transform that data into usable data, or clean the data, scrub the data, all these different things that you have to do before it's usable, before you can actually get insight from this data. And one other key aspect is it's got to be reproducible. The number one thing that I hated at my job when I first got there was using Excel and Access and having instructions in a Word document and having to find all these different things to figure out how to reproduce a document. Or you get a PowerPoint slide that has a graph on it. 2 years later, someone says, can you reproduce this PowerPoint slide? I don't even know where the data came from. So that's why I'm really excited to bring R and Python and all these different tools to Tinker. And we now have the ability to do that, so that's good. And one term that I learned throughout this process was ETL, extraction, transformation, and load-in. I didn't realize that was kind of a buzzword, a keyword to look for. As my job search was going, I started looking up ETL engineers. And what I found was that's a really good fit for the stuff that I'm doing right now. I'm wrangling data. That's all I'm doing. I'm pushing data from one point to another and wrangling it, making it more usable. So what we're going to deep dive into the code here in a minute is I'm going to talk to you about these different facets of the pipeline. The loading the data, the different types of files. You've got CSV files, Excel files, access files. It could be straight to a SQL server. Some data pre-processing and exploring the data. It's super crucial, and it's usually overlooked if you want to just jump right in. That's what I tend to do. I overlook the stuff you're supposed to do because it's not as fun. But let's get through that hurdle. Correlation plots to help explore data. We're going to talk about scatter plots. I'm going to talk to you guys about outliers and what to do with them. A lot of lingo out there saying just remove the outlier. That's not always true, so I'll get into a little bit of that. A little bit of normalization of data, why I'm going to combine my training set with my test set, and another big one is the NA values. NA, not applicable, whatever it might mean to you. I'm going to talk to you about that because that's kind of a big deal. When this is all said and done, though, we're going to pipe all of this data into models. The whole point of doing the data cleansing and the data cleanup and the transformations is so that I can pipe these into a multitude of models without any issues. And so that's the hard part is you have this model that you want to use, some XGBoost model or some machine learning model. And yeah, it's great if you can just type it into the function, but the data is not in the right format for it, and that really is a showstopper. So the whole goal is to get it into that right format. So I'm going to start with, I'm going to talk about the correlation plot. And a correlation plot, this is a messy one. I'm sorry I didn't clean it up too much more than that, but a correlation plot is going to give you correlations between variables. And what you see here is anything that's in the red range or the very blue range are going to be either positively correlated or negatively correlated. And what this correlation plot gives you is an idea of where to start. You know, you could possibly start where the variables are correlated in the red. For example, I know it's hard to see on here, but a red one is where the, you can see the red ones, but if you line up those variables, you can say, hey, I want to look at those variables more closely because why are they correlated so closely? So let's get a deeper dive into that. And so that's what I did here with the, this is the I forget what it is, but GRT live area versus the sale price, right? So they seem to be correlated according to this plot right here. So I wanted to look at it. So at the top is the original plot without any cleanup. As you can see, there's a couple of outlier looking things out there. So there's a couple things you can do about that, and I'll talk to you about that. On the bottom plot is imputed outliers. So what I did in this case was I took all of the data and I figured out the interquartile range of the data, and if anything was 1.5 times further out than that on either the left end or the right end of this plot, I actually capped it at that interquartile range. So if, for example, if most of my data was between like 5 and 6, and then all of a sudden I had a 15, I'd want to cap it at somewhere around 6 at the max, right? Why is that 15 out there? I could have gotten rid of that 15, but instead I decided that that data was probably wrong, and I capped it. This chart might demonstrate that slightly better here. So with outliers, you can remove them or replace them. What I did was I used the interquartile range instead for most of them. And then there's this mode thing, the neighborhood example. That example is if you have, like this is housing data. I'm sorry if I didn't explain that first. The mode of, for example, what type of zone are you in? Are you in a commercial zone or are you in a residential zone? Things like that, right? Well, if most of your neighbors are residential and all of a sudden you have one that's commercial in the midst of it or blank, you might want to impute whatever the most occurrent frequency of that neighborhood is, which is residential, things like that. And so on the bottom, you have that interquartile range deal, where 50% of your data is to the left, 50% is to the right. And so basically, Q3 minus Q1 is your interquartile range. If anything lies 1.5 times that distance out, I cap it at those Q3 or Q1, depends if it's on the left or the right. Doesn't mean it's correct, it's just one way of doing the data analytics and imputing outliers. So this is the NA fun stuff that I like to look at. I learned this recently. NAs are usually troublesome and I don't really like them, right? So what I've been reading about with NA values is NA doesn't mean NA. It doesn't mean it. See all these different variations of NA I have. NA, N/A, not applicable, no answer. What does it mean? So to answer that question, you have to know the data. You have to get a data dictionary, or you have to know who's inputting this data, know what the system is like, right? So, and that's crucial. So normally, we would think that it's just not there. Maybe we should get rid of that whole entire, we use na.omit in R, but turns out that column had 90% NAs, so there goes 90% of your data. So we don't want to do that. Another option would be to delete that column or that feature altogether. So you can do that, and there goes that feature, right? One thing you could do that I thought was pretty interesting was if you have two features that are similar, or they're like multi-collinear, so if you have like bathroom square footage and you have bathroom something else, like just the fact that there's a bathroom, they're almost always going to be the same, right? So maybe the square footage is a bunch of NAs, but the fact is they have one bathroom or two bathrooms is what really matters, right? So you might want to choose one feature to get rid of over another, the one with the fewer NA values. That's probably a poor example, but if two features are similar or multicollinear, the one with the fewer NAs might be more usable, and you can just get rid of that other feature. It's just an idea, though. Again, like none of this is foolproof. This is just ways to generate ideas and to experiment. And so I wanted to show you guys this library that I found recently. It's called NANIAR and Upsetter. I thought it was pretty cool. I found it on like Stack Overflow or something. This is just an example of what it can do. If anything you can get out of this is those two libraries are pretty awesome. What it shows you is the intersection of NANs across features, or NAs. So on the bar chart that's going up vertically, you could see that there's dots beneath them. If there's a dot there, that means that there's that many NAs that intersect with those other features that are on the left. For example, the fence NA intersects with, let's see if I get this right here. It intersects with all of the features on the very right-hand side, but the amount of times it intersects with all those features, the NAs, is 1,077. It's on that bar chart. And that really tells you a lot about the data pretty quickly. So I thought this library called Upsetter and NANIAR was super easy to look at NAs in a different fashion. So with that being said, since that NA intersects with all the other ones, you've got to do some cleanup for sure. Okay, so let me end this show. I've got more, but I'm going to go back to it. I'm going to show you the actual code and show you what I've done and where I got the code. So I got the code from Kaggle website, KAGGLE.com. And if you guys haven't heard of Kaggle, it's great for data analytics. You can look at other people's reports, other people's analyses, and follow their footsteps. And that's what I did. I took someone else's code and I forked it, and I tried to upgrade it and improve it my own way. At the same time, I had to understand what they were doing. So what I'm about to show you is a little mixture of both, and I'll walk you through some of that. And then we'll get back to the slideshow. Hopefully this works. Okay. So as you can see here, this is, it might be a little small. Let me see if I can blow this up just a tad for you. A little better. I'm not going to go through line by line. I'm just going to give you the general idea here. You want to load your data. So you have a training set and a test set. Kaggle is really pretty good because it'll actually break that set out for you. Typically, it'll have a training set already and a test set. And if you don't understand why you have both, there's a reason, because you can train your data with a certain data set, and you can test out your model that you create, your predictive ability, with the test data that the computer's never seen before. So it's a way to cross-validate your errors, is what it's doing. For that other graph? Yes. That's not all of the columns either. There's only so many combinations of NAs you can have. I think if there's 30 or 40 features, to find every combination of all features that intersect NAs, it's not really graphical. So you really have to narrow it down to like 5 or 6 features at a time and get a look for it. It's definitely a good package to look into it. I really liked the graph. I thought it was great. And I use something called data table. I've been used to using that. I read somewhere when I first started R, hey, data table is really good, use it. And so I started using it. Then other things pop up like dplyr, dplyr, and all these awesome things that you can use to manipulate data. But data table is my go-to choice for now. And what I do is I want to print out the structure of the data of the data table. And that's what I do here. First, I have the dimensions. That first line, the very top, is 1460 by 81. So that's 460 rows of data with 81 columns or features. And then if you see the second one, says 1459 with 80. So we're missing something in that test set. So that's why you want to check the dimensions of your data. Let's see what's going on there. And then also the structure of the data is what you see here. It looks messy, but it's every single feature and then what data type they are. This matters especially if you're new. If you see like on the second one down, the MS subclass, it says integer value, and they all have digits, right? 60, 60, 20. Well, is an integer really what it's supposed to be? Is that a code? Is it really supposed to be a factor, maybe? And vice versa. If it's supposed to be a number and it read it in as a character, you would be able to find that here. So you have to carefully go through all of your data structure and check all of them, and it's painful because there's data sets out there with 200 plus, 300 plus columns of data, and you have to actually go through every one of them. And so we're not going to do that today. Data preprocessing. This is kind of cool. The ID number is with this data, and realistically, the ID number has nothing to do with your predictive capability for predicting what the house sale is going to be. So that fact is we're going to get rid of ID number. It's gone. We set that to NA. Or we actually just set it to null. And then you saw this plot in the PowerPoint. Let me make this a little bigger. So like I said, you plot those, you kind of look for outliers. This is the function where I replace outliers. I believe I stole this one and I forgot to cite it, but it's from Stack Overflow, I'm sure. Let's see if it runs here. It gets rid of the outliers, and then when it runs, I've already run this, so I don't have to run it again. You see that top part where all the data points were capped. You can see it's kind of a line there. And I just did that arbitrarily for an example of, hey, this is one way to do this. But if you look at this, it looks like there might be a relationship between the sales price and the, I think, greater living area, so the living room size, and it looks like it could possibly be linear. Now, you can't use a subjective eyeball approach, but it could lead you down the path to check for linearity, check to see if they're linear related. And so here is the sales price by itself, and I did a histogram plot to see what the distribution is. The reason that you want to do that is to make sure that your distribution is what you think it's supposed to be. Like if it's supposed to be a normal distribution, it should match a normal distribution. Otherwise, all of your assumptions about predictive analysis based on the fact that it's normal might not be true. So the best I can do was copy what was already there with Kaggle, and they did a log transform. Let me see if there's two. Okay, so the one right here is the original data, and you see that it's not quite a normal distribution. And then when the log transform happened, it still, to me, does not look like a normal distribution. So this is an area where I'd like to try to dive in more and say, you know, what else can I do to this? Can I do anything to this? And then what is that outlier looking thing way over there, right? I haven't done all that, but those are the things that you're looking for when you do the normal distribution histogram plot here for the sales price. Okay, and I should have done this before, but I combined the training and the test set, because when I start removing features and doing all of the transformations, I want to do them to both the training and the test set to have a level playing field, I think. Especially if you're removing features, because you need the same amount of features for each one. So if you put them together, make sure you understand which ones are which so you can pull them apart later. That's the idea. Okay, so let's talk about the NAs again. I talked about all the different NA values and what they might mean. Let's see, we'll do an NA. I wanted to just pull out the very high NA value ones because there's so many NAs. But as you can see, these are percentages, and you know, something like the pool quality control number is like 99% NA. So I don't know how good that's going to be. Now, what does NA mean? Maybe it means there is no pool. You have to look at the data dictionary. And in fact, every Kaggle site should have a data dictionary, and this is the data dictionary for it right here. So you can look up every single one of these and find out what NA means, hopefully. It's not always going to be in your data dictionary. You might have to go ask the person that's inputting this data, but that's pretty crucial. Because what you could do is if you deleted that feature, well, maybe they didn't have a pool, and now that feature's gone, and that pool would have been a really good indicator of maybe your house is worth $10,000 more than if it didn't, right? That's just the idea behind it. So just be careful with what you drop for NAs, because I was doing it wrong. I thought NAs were no good, and just get rid of them if you can. So now this is pretty interesting here. To get rid of some NAs, we're going to replace them with a none variable, like fireplace, none. So that way it's no longer an NA, it's an actual none variable. So you have to go through your list, the alley, pool quality, miscellaneous feature. If it's none, put none, not NA. NA is a special data type, and a lot of the, especially the machine learning algorithms, do not like NAs at all. And so this is the part where the neighborhood I was talking about, getting the mode. I basically said, hey, what's the mode of each neighborhood? And if there's any NAs in that data, replace it with what the mode is. Arbitrary, but I think it works pretty good. And then, of course, missing data that you want to replace with zeros. So taking care of those NAs is a big part of your cleanup, is basically what I'm showing you here. So the garage year built, that one should be in this category, but garage area should be 0 if there's no garage. So things like that you'd want to look at. And so that's what I do there. Let me go down to the factor data. I thought this was very interesting. So in Kaggle, this was already created, except there was no designated way to sort these. I created a function that will actually give these values of integer values instead of the actual factor data that it is. Because what's worth more, red or blue? It's a factor data. They're both equal, right? So how do you set those levels is basically what I'm doing here. So in a fireplace, if there's none, I want to create a level of maybe 1. And then if there's a poor quality fireplace, a level of 2, and so on. But I want them to be in order. This is just an idea. I'm not sure if this is a good route to go or not. So it's, you might have heard of one hut encoding. So basically, how can I use factor data as numerical values? Because maybe they have significance, is all I'm trying to get at. So the order of the levels is what I'm trying to get at here. And so what this function does is it creates each level right here. This function took me hours to figure out. And it uses, it's a function that returns a function. I forget the name of that, but it's really interesting. And what it does, it makes every single one of those factors into levels. So 1, 2, 3, 4, 5. And I can actually use that in my predictive analysis instead of as factors, where factors are somewhat arbitrary and equal. I'm not sure if that came across correctly, like if it made sense. So a fireplace or no fireplace is one way to look at it. But if you have a poor quality versus a good quality, and you can just kind of weigh that as a 5 versus a 2, when you run your analysis, you can use that data as actual part of the math instead of just a none or it's got 1. Okay. And I'm going to go back to the slideshow now. Hopefully that'll work. If I can find it. Let's see. So I ran into some problems at my actual job, and one problem was the data set was way too big. So I had 21 files, and each one was about 1.6 gigabytes. And if I tried to load these into R and bind them together, it was quickly going to get way too big for my RAM. So this is where I had to learn about hardware and how this works with the RAM versus the disk. And so what I did was I made a loop go through each file in that directory, and I would load one at a time, and then I would filter it for the things that I definitely want to keep, and then I would run through the next file and bind it. I would R-bind it to the next file. And so that way, I kept my data size a lot shorter. This would quickly run into problems with RAM. So that's how I solved that problem. I used data table for one, and then I used a for loop and filtered what I didn't need out. And by the way, I don't know if you can do it with a data frame, but with a data table, when you read in the data, you can do a select statement just like in SQL, and you can select the columns that you want. So I believe that it won't load those other columns into your RAM to fill you up. So what I've noticed now, just recently in my work, is I'm running out of RAM quickly because I'm not careful with what I load into it. I'm not careful with my garbage collection, my data collection, things like that. So it's just a little tip. Okay, so I don't know if anybody's heard of ODBC library, but I use that to connect to Microsoft Access. Well, in the government world, we have 32-bit access, and I have a 64-bit R. And there are some workarounds for this, but the easiest way to connect a 64-bit R to a 32-bit access database is to actually go into your global settings and change it to 32-bit. It's a terrible workaround, but that's what I have to do. There's ways to do it where you can save an R data file, open up an R session with this 32-bit, capture that data, save it as an R data file, go back to your regular R, all in a script. So, I mean, eventually I think that might be the solution. A better solution would be to upgrade my Microsoft Access to 64-bit, but that's just something I ran into, and if you ever have troubles with ODBC, make sure you check to see what kind of, is it 32 or 64-bit? Good practice is to keep your raw data into like an input file or somewhere where it's never touched besides when you initially got it. And one thing that I like to do is when I start spitting out CSV files or R data files or any type of file, I like to append like the Julian date onto it, so I always have an archive of that record of that day's file, so I can always go back to it. It's just an easy way to do it, and if you do that with code, it's a lot quicker. And of course, what I do is I separate my transformations and my data cleanup from my actual visualizations. And I was talking to some others earlier. I use Flex Dashboard for visualizations because we can't use Shiny apps. But Flex Dashboards is pretty good. I think they're nice. And I use R Markdown, of course, as well, to try to keep it all reproducible. And with that being said, I think that's about all I have. So if you guys have any questions or questions about Tinker or anything about my job, I'd be glad to take them. So the forecasting, he asked, I did forecasting earlier in my career. What kind of tools and software did I use for that? So in the Air Force, we have lots of legacy systems, lots of legacy software that all work together, and they try to do predictive forecasting for you, but basically my job was to find those outliers, to find those NAs. So for the most part, the software did it, and it's legacy systems, so it would be like a system called D200A and DO43, DO75, all these different systems that work with budgets, maintenance constraints, capacity constraints. It works with scheduling, dollars, everything. So then what I did when I say forecasting, I was actually looking more for the outliers and the NA values, and then trying to figure out why the system didn't actually overlay correctly. But no tools such as anything modern. Any other questions? Well, I hope that this is a good start for maybe doing something like this at lunchtime, because it's a good time for me to come out. And maybe in a few months, when I learn more about this stuff, I can come back and really impress you guys with something new, maybe some machine learning algorithms in there, maybe the actual predictive part of this. Or what I'd like to see is some of you guys that have been doing this for a while, I want to learn from you for the next time and try to mimic what you guys are doing. So I appreciate your time.